swapping and paging out. And this is a critical situation memory management. So what happens when RAM is completely full and a new page still needs to be loaded? The system cannot stop. It cannot say no space available. Instead, it makes a smart decision. Here, the core idea is when a physical memory is full, the operating system must remove or evict a page. And this process is called paging out, or in simple words, swapping out. How does the OS decide this? The OS does not remove pages randomly. It uses intelligent strategies. What we saw, few of them as page replacement algorithm. Most of the common is least recently used. What does LRU does? LRU looks at usage history and asks which page has not been used for the longest time. The assumption is simple. If a page hasn't been used recently, it is less unlikely to be needed immediately. Let's walk through what actually happens here. The OS identifies the page in RAM that can be removed. That page is written into a swap area on the disk, which ensures that the data is not lost, just temporarily moved. The corresponding frame in RAM is freed. Now space is available for the new incoming page. The page table is updated. That is, the removed or evicted page is marked as not present in RAM and said that it is available on the disk. So when I refer to my example earlier with reference to library, when your disk is full, librarian notices a book you haven't touched for a while. That book is taken back to the shelf. Space is freed on your desk. A new book is brought in, and you continue working without worrying about the swap happening behind the scenes. This process involves disk I/O, which is slower than RAM. So the OS must choose wisely, remove the right page, minimize the unnecessary swaps, and keep frequently used data in memory. So paging out means what? Making room in RAM by moving less used pages to disk. And this is how the system maintains the balance. So limited physical memory is balanced that way. Unlimited virtual demand also is balanced. And now next logical question is, how do we measure the efficiency of these decisions? What happens if too many pages are swapped in or swapped out? And that leads us to a concept like thrashing and performance optimization, where memory management can either shine or struggle. So let us try addressing benefits of virtual memory and paging. Now we understood how virtual memory works, how paging works. Let us step back and appreciate why this mechanism is so powerful. Because everything we have discussed so far is not just theory, it directly enables the smooth modern computing experience we rely on every day. That is, first, probably you are executing larger programs. We can run programs that are larger than the physical RAM. You can check like your operating system code. Rather, if you see the binaries, your whole operating system may be in GBs. The amount of RAM probably may be small, some 8, 16 GB. But your code is more than that. So without virtual memory, a program must fit entirely into RAM to execute, which will never happen if virtual memory is not there. But with virtual memory, only the required pages are loaded at a time, and the rest can stay on the disk. And this means large applications can run, complex softwares can run, even memory intensive tools can run seamlessly on a limited hardware. Second is multitasking. Now think about how many applications you run at once: browser tabs, editors, media, background services. Virtual memory makes this possible. It allows multiple programs to stay active simultaneously. Each program gets its own virtual address space. Even if RAM is limited, the system dynamically loads and unloads the pages, keeps everything responsive. So you can switch between the tasks smoothly without choosing or closing one to open another. Then suddenly a question arises. The critical safety feature, something called as memory protection. As we know, each process isolated in its own address space. What exactly it means? One program cannot accidentally overwrite others' memory. The errors may remain contained. The system stability can be improved. So if one application crashes, it does not bring down the entire system. Fourth is efficient sharing. That is the smart optimization, where multiple processes can share the common code. For example, shared libraries, system files, common functions. Instead of loading multiple copies into memory, the OS loads it once, and it allows multiple processes to refer the same pages. And this saves the memory and improves the efficiency. So one powerful system, virtual memory and paging provides flexibility, efficiency, protection, and scalability. So virtual memory is not just about extending memory. It is about optimizing how memory is used, shared, and protected. And that is why it forms the foundation of every modern operating system. So from your laptops to your servers to even your smartphones. This invisible mechanism is constantly working. So everything feels smooth, powerful, and effortless. Now let's explore a smart optimization that makes virtual memory even more efficient. And this concept is called as demand paging. Instead of loading an entire program into RAM, the system loads nothing in advance. Yes, nothing. You might be wondering why I said nothing. Pages are brought into memory only when they are actually needed, not before, not just in case. So when a program starts, its pages are not immediately loaded into RAM. As the program begins execution, the moment it tries to access a page, if that page is not in memory, a page fault occurs, and only then your operating system loads that specific page from disk into the RAM. So memory loading happens on demand, and and that is why it is said to be powerful. Think about this: like in many programs, not all parts of the code are used immediately. Some parts may never be used at all. So without demand paging, the system would waste time loading everything. RAM would be filled with unnecessary data. But when the demand paging is there, only the required pages are loaded. Memory usage stays lean and efficient, and startup time becomes much faster. Let me go back to our library example. Instead of placing all books on your desk before you start, the librarian waits. You begin reading, and only when you ask for a specific page, it is brought to you. So your desk stays clean, and you only deal with what you truly need. Demand paging introduces page faults during the execution, but overall, it reduces the unnecessary work. It improves the responsiveness and optimizes the memory utilization. This is not just a concept. Most modern operating systems use demand paging by default because it provides a perfect balance between performance, memory efficiency, flexibility. So demand paging means load only what is needed, exactly when it is needed. So it is like simple idea saying load only what is needed exactly when it is needed. But it is one of the key reason why your modern systems feel fast, responsive, and efficient. And once you understand this, you begin to see virtual memory is not just about the illusion. It is about intelligent decision making at every step. So let us visualize now thrashing. Let's talk about this situation where everything we have learned starts to break down. And this phenomenon is called as thrashing. What is thrashing? Thrashing occurs when the system spends more time swapping pages in and out of memory than actually executing the useful work. Let's visualize this. Imagine a graph in your mind. On the x-axis, there are number of processes. And on y-axis, there is CPU utilization. Initially, as we increase the number of processes, CPU utilization increases, system performance improves, and resources are used efficiently. But only up to a certain point. Suddenly, the graph drops sharply. The CPU utilization plummets. Why? Because the system enters into thrashing. What happened internally? There are too many processes. Each one needs memory, but RAM is limited. Correct? So when RAM is limited, ultimately, what has happened? What your operating system is doing, constantly swapping the pages in and out, handles frequent page faults, keeps accessing the disk again and again. And remember, disk IO is much slower than RAM. So instead of doing real computation, the CPU is waiting for pages to be loaded, waiting for the disk operations to complete, and this leads to wasted CPU cycles, severe slowdown, and poor system responsiveness. So imagine again the disk, which is overloaded. You keep asking the librarian for new pages, but every time a new page comes, another one must be removed. And this keeps repeating. So instead of studying, you are spending all your time waiting and swapping books. And that is thrashing. And this is dangerous. Thrashing can create a false sense of activity. The system looks busy, but is actually doing very little useful work. How can we fix it? Practical solutions are like increase the RAM. More physical memory reduces the need for constant swapping. Or reduce the number of concurrent processes. Pure processes means less competition from memory. Or third reason is, or third practical solution is use smarter page replacement algorithm. Better decisions reduce unnecessary page faults. So thrashing means too much paging, too little computing. And it is clear signal that system is overloaded. Memory is being mismanaged. And understanding this helps us answering a deeper question. Now, just how memory works, but how to balance the performance and resource usage efficiently and effectively. Because in operating system, efficiency is not just about doing more work, but it's about doing the work, rather right work at the right time. Now let us understand the modern implementations. Let's bring everything we have learned into the real world. Virtual memory and paging are not just theoretical concepts. They are the foundation of every major operating system today, from desktops to servers to smartphones. This mechanism is constantly working behind the scenes. Let us talk about Windows. Microsoft Windows operating system. Windows uses a page file stored on a disk. This acts as the extension of RAM. You can search that page file. The key point here is it is automatically managed by your Windows kernel. You don't have to manually control it in most of the cases. So the system dynamically decides when to move pages, how much space to allocate, and how to balance the performance. Now, when we talk about Mac OS and Apple operating system, Mac OS takes things a step further. It uses memory compression. Before moving data to the disk, it tries to compress pages in the RAM itself. If more space is still needed, it uses swap files. And this approach reduces disk IO, improves responsiveness, and makes the better use of available memory. That's why you might have realized comparing to Windows, Mac OS is faster. Third is operating system is Linux operating system. Linux is known for its flexibility and control. It supports, you must have seen rather, swap partitions, swap files, correct? And unlike other systems, it is highly configurable. You can configure everything. As an administrator, you can tune swapping, how aggressively swapping happens, what are the memory policies, and even you can decide or tune the performance behavior. And this makes Linux suitable for servers, high performance systems, custom workloads. Even if you see most of the cloud servers are running on Linux. I'm not saying all. Email services are also running on Linux. And lastly, mobile systems, iOS and Android. Now let's look at these mobile platforms. iOS Apple mobile operating system and Android mobile operating system. These systems face a unique challenge. Like you know, there's a limited memory and flash storage, which has a limited lifespan. So instead of heavy swapping, this rely more on memory compression, intelligent memory management. Traditional disk swapping is minimized to protect storage, improve battery life, and maintain responsiveness. So across all these systems, the core idea remains the same. Virtual memory creates the illusion. Paging managers or manages memory efficiently, but each system adapts the strategy as discussed and optimizes based on the hardware and its use case. So virtual memory is not just a concept that we are studying. It is a living system actively shaping how every device we are using is performing. From my laptop or your laptop to your phone to large scale servers. And this invisible mechanism ensures everything feels smooth, responsive, and powerful. Now let us conclude by this last slide. As we come to end of this journey, let us take a pause for a moment and reflect on what we have uncovered. And that's why I have given a title as the invisible powerhouse. Throughout this session, we explored virtual memory, paging, page tables, MMU, page faults, page replacement algorithms, demand paging, thrashing. Each concept seemed like a separate piece, but together they form something extraordinary. The silent engine behind everything. Virtual memory and paging are truly the unsung heroes of modern computing. They don't appear on your screen. You don't interact with them directly. Yet, they are working silently beneath every application that you open, every browser tab you switch to, every process running in the background, transforming these limitations into the power. Remember where we started? We started with physical memories limited, but through the intelligent design, that limitation is transformed into flexibility. And what was once small, finite resource becomes a system that feels large, continuous, and almost limitless. This is not just memory management. This is the engineering and illusion so perfectly that user never questions it. Think about today's world, running complex applications, handling massive data sets, designing AI applications, switching between dozens of tasks instantly. None of this would be possible if programs had to fit entirely into the RAM. None of this could work if processes interfered with each other. None of this would scale without efficient memory handling. So when you use your devices, like handheld devices, like mobiles, laptops, or even your computers, next time, pause for a second. And behind the smooth experience, behind that seamless multitasking, there's a system continuously and constantly managing memory, moving the data, making the decisions, and maintaining this illusion, all in the real time. So virtual memory and paging are not just features, they are the foundation on which modern computing stands. And without them, the computing world as we know it simply would not exist. And now, remember, you don't just use a computer, You understand the invisible powerhouse that makes it possible. So here we end this part.